I want to give some examples of how Flash architecture has helped me set up a completely new problem, build new physics into Flash, and extend its capabilities. And hopefully I'll emphasize how the way we do things in Flash makes this easy, or at least easier, and makes it maintainable, and makes it extensible, and makes it just easier for the programmer, easier for the application designer, easier for the user. If you got any questions, again, just raise your hand. I'll try to spot you somewhere in this room. And I might defer for some questions to Anshu about what's going on. So Flash rules help. And Anshu talked about the rules that we have in Flash for coding, for standards, for naming conventions, for data ownership, and the arbitration process that goes on for different sets of data. The use of inheritance is very powerful in our architecture, and we can use that for setting up new physics, setting up new simulations. And it helps to reduce code duplication, which code duplication is a nightmare. It's a pain. And so anytime you can reduce code duplication, that's a good thing. Things like the naming conventions and how we name variables to signify what unit owns that variable or that piece of data is also really helpful when you're reading the code. It makes variable names this long, and we have actually literally hit the Fortran limit for some variable names on some compilers. But it makes it very clear what you're looking at. And I love use-only statements. Blanket use statements, I hate, right? Because you don't know where a piece of data is coming from unless you specify it with that only statement, especially when you're looking at module scope data. This is really, really useful. Some of these things can wind up to be a bit tedious because you're typing more, but it's really worth it. So for my problem, what kind of things did we need to run a core collapse supernova problem? Well, we needed higher order shock capturing, self-gravity, a realistic equation of state that had a lot of physics in it, electron capture physics during the collapse phase, some sort of neutrino physics, and I'll talk about two different approaches to the neutrino physics, being very simple neutrino heating and cooling, which is completely local, and then more sophisticated neutrino leakage, which is an approximate transport method. And we also needed multiple concurrent setups without code duplication, meaning I wanted to be able to run multiple instantiations of my problem that use slightly different physics without a lot of overlap in the amount of code that I had to duplicate. So in Flash, we had higher order shock capturing MHD and self-gravity, as well as the architecture allowed us to use multiple concurrent setups without code duplication, but we needed to implement some new physics in the code. So the first stuff I'll talk about is the sort of local source terms, the electron captures during collapse, and local neutrino heating and cooling. So if we take a look at a Flash source code structure, this is the source terms unit, which is underneath source, physics, source terms. And this is something I think Anshu mentioned. But the naming convention here is also very important because lowercase directories in the Flash tree signify that those are just for organizational purposes. Those aren't units in the sort of membership classes that Anshu talked about. Those aren't units, those are just organizational directories. Now anything with a capital, leading capital, that's a unit. So burn, heat, cool, ionize, stir, those are all source terms and they're units. So within those units you're going to have subunits and multiple implementations of various things. So what we needed to add was a new unit at this level called deleptonize, which is a short word for electron captures. You're losing leptons. And then within heating, we needed a new unit, which was, this is a subunit now because it's underneath of a main unit, neutrino heating. And that's, we needed to add these two new features within the source code architecture. So let's talk first about neutrino heating. Now, since this is a subunit underneath of heat main, the driver already has the hooks to call heat.f90. So we're replacing heat.f90 with our own implementation of heat.f90 within the neutrino subunit. And so that's going to overwrite the default implementation, which if you haven't included heat is just a stub. So that's where the physics is going to go on. Anything that's a capital here, heat, the hooks are already there in the code because this is an alternate implementation of an existing source term, the heating source term. One little thing here, there is this thread block list subdirectory, which again, it's lowercase, so this is just an organizational tool. This contains an alternate implementation of our heat.f90, which has a different threading approach than the one that's under Neutrino directory main straight away. And we can switch between these different threading approaches within our config file by using a setup variable thread block list. And if that thread block list setup variable is true, we're going to require this subdirectory, which contains an alternate implementation of heat.f90, which will overwrite our version of heat.f90, which is in the main directory. And so you can use these subdirectories and this setup syntax in the config file to have alternate implementations of things like this that you're trying different approaches with. You could include them separately in principle if you set your config file up. What are you thinking about specifically? I mean, or just generally, abstractly, separate heating terms that are not dependent on each other could all go into heat.f90 if you wanted to. Or what you could do is you could have, and this will be more apparent I think in the other directories, you could have local functions which are called by heat.f90, each one of which contains your separate heating terms, right? And they'll be local in the sense that they're not capitalized and they don't publish a public API that other units could call. So they'll only be called from within the heat unit so that they're local in that sense. And they could contain separate bits of physics that are distinct from each other that heat.f90 would call individually. That's one approach to doing that. And you'll see in some of the other things I talk about, I do just those sorts of things. It's not different heating terms, but you've got your main public function calling local functions that do different physics. Okay, so now deleptonize is a bit different. Neutrino was an alternate implementation of an already existing unit, heat. Deleptonize is a new unit. So for deleptonize, the hooks need to be added to the driver in order to call that new piece of physics that didn't exist before. So if we take a look at this, within deleptonize, we've got, of course, a config file, and we have all of these public functions, which start with the capital D. Deleptonize, finalize, all of this stuff. Now, since deleptonize is a unit, it has to have the deleptonize main subunit, which is its primary implementation. Now, at this level, at the level that deleptonize main exists, all of these public functions and routines are stubs. They're no-ops, right? Just like Anshu talked about. This is so that if you don't include deleptonize in your simulation, you don't care about electron captures, what will be compiled into your code is just stubs. It'll pick up these stubs. So if we look at deleptonize main, this looks a lot like deleptonize in terms of what files are there, but here the actual implementation exists. These aren't stubs. These are the guys doing the work. And we have an example of what you're talking about here. So the public functions, starting with capitals, for instance, deleptonize. Deleptonize unit, not only does it calculate the electron captures, it does something else. It monitors the core conditions and tells me when something called bounce has occurred. And this is a transition in the physics. And I just want to know when it happens because some of the physics changes and I want to turn certain things on and off. Now, deleptonize is going to make a call to this under lowercase delep detect bounce. This is a local function. Only deleptonize can call this. Only the deleptonize unit can call this. It can't be called by some other unit in Flash like grid or hydro, right? It doesn't publish a public interface, only a local interface. So delep bounce will basically return a logical, hey, have we bounced or have we not bounced? That deleptonize can use, and that will exist in deleptonize data. Now, this information about whether or not the core conditions have reached what I consider bounce is important to other physics units, like the neutrino heating and the neutrino leakage scheme. So what I do, because this information, which is simply just a logical, basically, exists within this unit's module data, is I have written a public interface, deleptonize get bounce.f90, which publishes a public interface, and all it basically does is return whether or not this logical is true or false, right? But this is a way for another unit, like neutrino heating, to access the deleptonize unit's data through an interface without immediately, without directly touching its module data, which is a no-no. And I mentioned that we have a local API here. This is a stub implementation of delep detect bounce. This would only really be important if there were alternate implementations of deleptinize that might not actually do this delep detect bounce business. But this is what that would look like within the local API directory. Okay, so that's the physics of deleptinize. How do I get the rest of Flash to actually use this? Well, that happens in driver. Driver is the thing that brings it all together, calls the various physics units, calls the various infrastructure units, and puts together your simulation. Within driver main, there is a driver underscore source terms .f90, and this is the routine that's calling all the various source terms. And so in order to implement this deleptinize new source term, fundamentally new source term, into Flash, I simply had to add the hooks in source terms, driver source terms, to call deleptinize. I use its interface, and I call it. And there's also a similar call to deleptinize init in driver init source terms, which I just left out. But that's it. And now, if you're not using deleptinize in your simulation, it won't build in the deleptinize unit, just the stubs. And so this will call a stub. It'll be a no-op, but it won't crash your code. It will compile, and it'll work. And of course, if you're using deleptinize, that calls something that does some physics. Questions about source terms before I go on? I'm going to talk about EOS next. Yeah. These are local source terms, so yes. I will talk about, actually, I'll talk about my neutrino leakage scheme is parallelized differently than this, these local source terms, because it's not local, and it has a sort of radiation grid on top of the main hydro grid. And so I'll talk about how I approach that, and I actually have a different parallelization scheme from the standard AMR scheme that we use in Flash, and I have to instantiate sub-communicators outside of the main mesh communicators that Flash uses in order to parallelize that routine and those routines. So I'll talk about that a little bit, and maybe that'll give you some idea. These are completely local. Everybody that owns a block runs this, right? Owns a block of grid data, runs these. Okay, good question. So let's move on to realistic equations of state. So the core collapse equation of state has contributions to thermodynamics from baryons, protons, photons, degenerate and relativistic electrons and positrons. And the baryons experience a phase change above about 10 to the 12 grams per cc, very high density, right? This is nuclear density, right? So I call this the nuclear equation of state. When they get packed that tight, the baryons experience repulsion because the strong nuclear force becomes repulsive. And this is very important to the physics of core collapse. When that happens, a shock gets launched, and that's what I call core bounce. I've referenced this in the deleptinize unit. When that phase transition happens, that's bounce. And it's a very important thing to capture in the physics. Traditionally, this equation of state has been used by table lookup because the calculation of the nuclear response and the nuclear force models is pretty hefty itself. And to do that on the fly is really expensive. The same goes for the calculation for the degenerate electrons and positrons. To calculate that on the fly involves a bunch of Fermi integrals, exponentials all over the place. It's actually pretty expensive. So that's also done traditionally by table lookup. We also have some other requirements for the core collapse equation of state. There's several nuclear force models, so we want the ability to swap in different tables with different force models at runtime. We don't want to recompile the code. Also, I got the kernel implementations for this equation of state from my collaborators, and they're publicly available at stellarcollapse.org. So what I wanted to do with this equation of state that I had from my colleagues was write wrappers in Flash that would access their routines in a way that allowed me the least amount of work possible, but still worked, was still fast, and integrated well with Flash. So we take a look at the EOS unit. Underneath EOS main, there's several different equations of state which look pretty common, right? Gamma law, multi-gamma, Helmholtz is the electron positron equation of state. Tabulated, which you think I might have used, but actually when I started all this, tabulated didn't exist yet. So, and multi-temp, which is a different multi-temperature equation of state. So we added this new nuclear equation of state. subunit within equation of state. So this contains a config file telling how to set it up, and these new local to the EOS unit routines, init nuclear, loadends, and EOS underscore nuclear, which does the main physics driver. Also here we have this kernel directory. Now the kernel directory is where I put my colleagues' code, right? I didn't change hardly anything to do with their code. I put it under kernel, and a kernel directory in Flash signals that, hey, anything beneath this level doesn't obey Flash standards and probably wasn't at one point part of Flash. So all bets are off once you get into the kernel level. So the way this works, let's see. So you look in the config file, and you specify in your config file that the default implementation here is the kernel, which means it's going to bring in those codes and those routines from kernel and compile it in your application. And what lives at this level that we're looking at is just the routines that I wrote as an API wrapper around those kernel routines. Now, these need to be added to the equation of state routines in terms of their calls. The hooks need to be added in to the top level EOS routines. And so all we had to do was go into EOS.F90, which lives in EOS main, and EOS.F90, which is a pretty low level routine compared to what some of the other ones Anshu was talking about, like EOS wrapped, EOS 1 point, EOS, all of these other things. Eventually they all call EOS.F90. And so EOS.F90 is the one that's calling the various physics models for your equation of state based on whether or not you're using that equation of state. And so right here we just added the call to EOS nuclear, which does some physics on your EOS data and returns some information. And then we put the same thing in EOS init, calling the EOS init nuclear. So added these hooks, and now we have a new equation of state. So going back to the directory, I have this public routine here, and you know it's public because it starts with a capital E. This didn't exist before in Flash. This isn't a re-implementation of something that lives at a higher level. This is a new routine. And what I needed was there was some specialized data in my equation of state that isn't in most equations of state. And so the EOS unit was not carrying this data around. It wasn't returning this data to other units that were calling the equation of state. But I needed this data for some of my physics. So I wrote a 1-point equation of state call that accesses these routines within this directory and then returns the specific information that I needed for my other physics. And so that's what that guy does. He's a capital E, so he has a public interface that other units can use and then get access to this equation of state data. Questions about equations of state? It is a very complicated unit, but it can be done to implement your own equations of state. And it's getting better with things like tabulated. Tabulated is newer and it's more abstracted, and so you can sort of substitute in, I think, more general tables. I think that's a bit of still idealistic at this point, but equations of state are just a complicated thing. And like Anshu said, everybody complains about equation of state unit and the way it's structured, but we haven't thought of anything better, and it works. And if you utilize the vectorization that's built in, it can be pretty fast. And equations of state get called a lot through the course of a simulation. So you want it to be fast, and you want it to be lightweight as much as possible. OK. So the last thing I'll talk about, which is quasi-transport for neutrinos, is neutrino leakage. Now, neutrino leakage supersedes some of the physics that neutrino heating and cooling does. So this is heating and cooling, very simplified local physics. Neutrino leakage is better physics doing the same thing, but using approximate transport. So these two units, this is an example of a case where you're doing the same physics with two different approaches. And we'll talk about how those two things mesh and don't mesh a little bit later. So basic overpicture, it computes approximate transport along radial rays embedded within the Cartesian domain of my Flash simulation. So this is sort of a spherical calculation within a Cartesian calculation. It's memory and compute intensive. So if we take a look at Flash's architecture, there's the rad-trans unit, which currently in the public release version just does multi-group diffusion. But it provides all the hooks that we need to do this neutrino radiation transport. So we added a neutrino leakage subunit within rad-trans main. And that contains our physics subroutines that does the calculation. Now, these capital rad-trans, the hooks already exist for these within the driver routine because we already have an implementation of radtrans main. So these are just overwriting those public routines with our custom routines here within Neutrino Leakage. And then all of the lowercase RTs are local subroutines, local to the radtrans unit, and they're called from, for instance, radtrans.f90, and they do the physics. They do the actual work of calculating the leakage, calculating the optical depths, and doing all of that stuff, sampling rays, remapping rays. They're doing the heavy lifting. The capital radtrans.f90, the hook already exists in driver, and we have a custom implementation of that does our neutrino leakage. Okay, so I mentioned that neutrino leakage has a different parallelization scheme. In Flash, the way it's typically parallelized on our block-structured AMR is the fundamental parallelized unit is the block. You know, you start passing out blocks to different processors. They've got their block of data that they compute hydro on, they compute source terms, they do whatever. But here, this is a non-local problem. And it's not really even logically Cartesian. So what I wanted was a different approach to calculating this in a parallel manner. Because in 3D, I'll have like 3,000 different rays, and to ask any one processor to compute all 3,000 rays was way too much work. It completely dominates the runtime. So what we did was instantiate subcommunicators, which Flash allows you to do. And taking advantage of module scope data, you can share this in a way that is local to that unit, and you've got a sub-communication layer within a unit that it can utilize to have a different communication pattern than what the grid structure pattern is implementing. So here, I mean, you can take a look at this code that I snipped out. Meshcom, RT Meshcom, is the main mesh communicator from the grid unit, which this is the local copy of it, stored within the radtrans unit. But what we do here is we split up this subcommunicator into, split up the main communicator into subcommunicators, and then pass out different rays to different processors within these subcommunicators. So what we're doing here is not just one processor per ray, or I'm sorry, one ray per processor. We actually have distinct subcommunicators, which are different groups of processes, different groups of ranks, which contain the complete set of rays. Because often, okay, I've got 3,000 rays, I'm running on 30,000 cores. If I pass out one ray to each rank, well, there's going to be a bunch of ranks sitting idle, doing nothing while the radiation is being computed. So what we have are subcommunicators that basically equal the size of the number of rays. So you're only communicating with a reduced communicator. Instead of the entire global communicator, which it might be 30,000 ranks, you've got 3,000 ranks along which you're communicating. And this calculation is duplicated amongst these different subcommunicators. But that's fine, who cares? They would have been sitting idle anyways. And you also reduce the distance that your communication has to travel, which is good for latency. This is an example of how Flash allows you to do these things. This is perfectly legit within the Flash architecture, and works out pretty well. We've got the physics that we need to do core collapse supernovae. And let's talk about having multiple setups of the same basic simulation without having too much code duplication. So to include new physics in your simulation, you can utilize, let's see, the unit rules and the inheritance rules apply to the simulation unit as well. The simulation unit is where you're going to store your setups and your applications and the rules for building those applications. And within the simulation units, you can have the coexistence of multiple applications that are based on the same basic setup by having alternate implementations just like you would in other units of Flash. So if we take the example of source simulation main, core collapse. So core collapse is a subunit of simulation, an alternate implementation of simulation main. So if we look inside there, we've got a bunch of routines, many of which start with the capital S simulation. And so these are your standard routines that you expect to find in any sort of simulation. They set up, init block is basically the initial conditions routine. Init does some basic one-time initialization stuff. Simulation data is a module that contains the local simulation data. But what we also have inside of this complicated setup are several superseding implementations of code from other units. Anything that starts with like grid, hydro, IO. These are all routines that exist and are owned by other units, and we are overriding those implementations by having our own custom implementation of these routines living inside of our application directory. So, for instance, mark, refine, derefine, I have a custom refinement pattern that I want to impose on the simulation that goes beyond what the standard grid mark, refine, derefine does. So I copy it into my core collapse directory, I make the changes that I want, and this is the version that will show up in my application when I build it. That goes for any of these other directories. And what we also have are subdirectories, which start with these capital letters, signifying that they are subunits. And so these are different variations on the core collapse setup. And within there, I have custom implementations of different routines that will only be used if we're doing these particular custom setups of core collapse. So how do we include our new physics that we just put into Flash, deleptonize the neutrino? Well, if we take a look at the config file, we've got several requires like driver. You've got to have the driver. You've got to have grid. You've got to have hydro and an EOS. And we've put requests on deleptonize, which is our electron capture physics, and requests on neutrino heating, which is our new heating scheme. That's how you would include these new things. If we've done everything right in implementing those physics in the Flash architecture, the build script will pick those up, put them in your object directory, and build them into your application. Let's take a look at a sub-alternate implementation of core collapse. So the standard core collapse setup does plain hydro with neutrino heating. Within there, we have magneto HD. You can guess what this does. This does an MHD version of core collapse, but it also does neutrino leakage instead of neutrino heating and cooling. So now we've got an issue where the parent unit is requesting something that conflicts with what we're requesting here. So if you take a look at the neutrino leakage config file, it explicitly says, I conflict with neutrino heating because we do the same physics and I do it better. So this will be a problem when you go to build. But you can get around that with some build setup syntax. But just before I go on to that, within magneto HD, if we list the directory, it's got its config file which specifies how it's different from its parent. You'll notice that I haven't duplicated in the config file, I need hydro, I need EOS. Well, it already knows that because it inherits that from its parent. All I'm saying in this config file is how am I different from my parent simulation? And we have a different grid mark, refine, derefine because for MHD, I refine things a bit differently. This will replace the alternate implementation that's in the parent core collapse directory. And then it has other alternate implementations of all those routines as well. So using setup syntax, we can get around this conflict. So the basic core collapse problem is set up using this setup syntax, which tells me that I'm using the core collapse simulation in 3D. Cube 16 tells me how big my blocks are. PM4dev tells me which grid unit I want to use. UHD opt is the optimized version of unsplit hydro, new impl, blah, blah, blah. We are threading within block. That's what the basic setup line looks like for the core collapse simulation with neutrino heating and no MHD. If I wanted to do the MHD simulation with neutrino leakage, I would modify this to say, okay, core collapse / magneto HD, great. Everything else would be the same. I would add this line, -- without unit, physics source terms, heat main neutrino. And since our parent unit core collapse only requested neutrino heating, didn't require it, it's fine with this. It says, okay, you're just requesting this unit. I don't have to build it in if you tell me not to at setup time. And that's what this will do. It won't build that unit in that conflicts with our neutrino leakage scheme. One other useful thing about the simulation unit is that it can break the law, meaning that it can, Anshu's looking at me, it can access other units' data modules. And where I do this is in IO write integral quantities. So write integral quantities spits out a bunch of stuff to a data file like total momentum, total energy, total cooling, total heating, all of these things. It's very useful. But it's also very useful for it to have access to other units' data. So it lives in the simulation unit, so it can access the simulation data. That's not against the rules. IO, it can access that. But then we get down here, where there is some stuff in the deleptonize unit that I'd really like to know and spit out each time step via write integral quantities. So I just go ahead and access that data. Now this can get hairy because it is not following the rules anymore of Flash. But it lives in your simulation directory. It's not implemented within the source structure of the rest of Flash, and so you can be aware of it, and if you're good, you can break the law and get away with it. So once you build one of these applications with, for instance, the setup syntax that I showed earlier, what happens is that the Flash build script collects all of the source code as symbolic links into one directory, all the source code that you're actually using in your application. So it ignores everything else that you're not building in. It points to stubs for things that you're not including in your application. And this can be very useful when you have alternate implementations of the same routine. For instance, heat.f90. You start to wonder, which heat.f90 is this actually pointing at? And you can look at your object directory and list it, and you'll see that it's all symbolic links pointing to the exact spot in the Flash source code structure that's the actual file that will be built in your application. And here's an example. You know, most of these other things are pointing at their respective unit. You know, hydro init is pointing at hydro init within the hydro unit. But IO write integral quantities, that special file, there is an implementation of this in IO that's very simple. But we have a more complicated version in Core Collapse. And so you can see right here, this is pointing at the simulation directory, where our simulation setup is. And so the object directory, the fact that it's all symbolic links, it's all a flat directory where you can look at all of these routines, is very useful. It's very greppable, right? If you're wondering, where is this variable initialized? If it's initialized. Where is it declared? Who owns it? You can go in here and you can grep around. You can find these things pretty quickly. Alternate implementations are really powerful. They allow a lot of flexibility and experimentation. They can almost act like pseudo branching, right? Where you take a piece of your code and you say, well, I want to do something slightly different. Copy, paste, and then you go to hacking. Use of inheritance is a good idea to reduce code duplication, but this model can get away. I think it's very good. It has tremendous power, but you have to be diligent because it can lead to some code duplication if you're not careful, which makes things more difficult to maintain, and ultimately long lag times in reincorporating code back into the main working branch. An example, which this isn't really all that bad, it's just something that we kept an eye on, was recently we optimized the unsplit hydro and MHD solvers, and we did this through alternate implementations rather than a traditional sort of version control branch. We didn't make a new branch that overwrote the already existing unsplit hydro implementation. We created an alternate implementation that existed within one branch of the code. And they diverged, obviously. And we are still working on bringing the optimized versions of MHD and Hydro back into the main working code so that it can be the default implementations of Hydro and MHD. The same thing kind of cropped up with threading implementations. So when we were first threading Flash, we decided to take multiple approaches to threading. Threading within the block, meaning the IJK loop was threaded, or threading on the block list, meaning that the list of blocks that a processor owned, it would be looped on, threaded on that loop. And we tried both of these things, and both of these implementations existed at the same time, along with a completely unthreaded implementation of Flash, which was the default. So now you've got perhaps 3 different copies of the same routine that do the same thing. The only difference is where the OpenMP pragmas are, if they're there. And that can lead to divergence in the code and difficult maintainability. That's better now, I think, in the code. There's just some caveats that can happen. I don't think it's really that big of a deal. Anyways, thank you, and happy to answer questions about Flash architecture and my experience with it. Thanks.